All right, so welcome to another fun-filled week of Trig. Before we get to homework questions, I see that Amber has a question in the chat about when are you guys going to get your exams? I could give you the shitty answer of when I get done with them, which is actually the real answer. I don't know exactly, hopefully by Wednesday. Normally in a regular kind of class situation, you guys would have had them back by now, but I'm noticing that grading takes me a lot longer via the computer. So anyway, that they're in the works, and hopefully I'll have them done by Wednesday. So anyway, so any other questions? How about homework? How's the homework stuff going? We doing okay with the identities? I know that we've done a ton of algebra, but yeah, go ahead, William. What's your question?
Sorry, one second. I was my son was like pulling my papers all around.
No
I gotta look it up real quick. I think it's like number 3 on 9 point whatever we just did. It was number 3 on 9.3.
Okay, I will go ahead and pull that up on my computer, and then we'll share it so everybody can see it.
Thank you.
But it'll just be a moment. So I'm going to go ahead and write that down just so I've got it. So number 3 on 9.3. All right. Anything else? Any other homework questions we want to look at? Like if there are any others from 9.3, I'll just make a list and then I can grab them all at the same time. My computer is being very slow this morning. All right, I think I finally got it up here. So let me go ahead and share my screen with everybody. Okay, so hopefully y'all can see my screen, and here's 9.3 number 3, and hopefully this is the one you want to see. It's also, just realize that yours could be similar to this one, but not identical. But it does say we want to use the half angle formula to fill in the blanks in the identity below. Okay, so we need, of course, to remember the half angle identity.
I'm sorry. It's actually number 4.
Oh, okay.
Yeah, but I mean, you know, if someone has,
that's cool.
Yeah, my bad.
Not a problem. Okay, so this look better?
Yeah, that's the one.
Okay, so these, we want to actually calculate the half angles, or the sine, cosine, and tangent for the angle, the half the angle of the angle that we're already given. So I'm going to do this one on the whiteboard, but let me go ahead and write down all this information, and I'll quit sharing the screen. We'll go to the actual whiteboard here. But for this problem, I've got that the cosecant of x is equal to 6. I also know that x is between 90 and 180 degrees. And then I just want to find all the halves. So sine of x over 2, cosine of x over 2, and tan of x over 2. Okay, so again, I'm going to quit sharing real quick, and we'll go to the whiteboard. Okay, so here's all of the pertinent information, everything that they gave us. And let's see if we can figure out what we got going here. So we should probably start with the half angle identities. So we developed these last time. And for each one of them, there was a plus or minus, right? So we had for sine of x over 2, we knew that it was equal to plus or minus the square root of, and does anybody remember what went in here?
First, I don't know about anyone else, but I can't see the screen. It's all black on my end.
The entire screen?
The entire screen, yeah.
I can see you.
Okay, yeah, Adam and Amber both just said they can see it. I know I can see it on mine.
Oh, crap.
So I don't know what to tell you, Vanessa. Maybe try to pin. Can you see everybody's, like if you go to, you know how they have the different views, like their speaker view. And if you have speaker view, you should be able to see the screen right now with the whiteboard. There's also gallery view, which shows all of the individuals. And in gallery view, you can also like click on somebody's picture to pin it. And then that way you'll see it. So I don't know if maybe you can get to it via that way.
I have like no settings at all. Maybe this is just a little messed up. I'm gonna leave the meeting and come back. Is that okay?
Okay, yep, totally. I'll let you back in as soon as you're back.
All right, thank you.
All right, so if we come back to this plus or minus, we end up with a 1 minus cosine of x, and that whole thing is divided by 2. So if we're going to calculate the sine of x over 2, we're going to need to know the cosine of x. And then we're also going to have to deal with this plus or minus business. Okay, so let's start with the plus or minus. Is this one going to be positive or negative? What do you guys think? Plus or minus? Okay, so William, you're saying negative. Mariola says positive. All right, sweet. So we already have a fight. So are we talking about the sign, the plus or minus? Yes. What is this going to be, a positive or a negative for the square root? All right, so here's how we have to do this. Let me just remind you. We have to look and see where is the half angle, not where is the angle whose information we know. I don't care about x, I care about x over 2. But knowing where x is helps. They tell us that x is between 90 and 180 degrees. So that's actually a second quadrant angle. But even if I didn't recognize that, if I just divide by 2, so I literally just divide all these guys by 2, I find out that x is going to be somewhere between 45 degrees and 90 degrees, which is a first quadrant. So in the first quadrant, the sign of sine, the plus or minus sign for sine, is positive. So I know that that's going to be positive. And in fact, I know that's going to be true for the half angle for cosine and for tangent. All of them are going to be positive because x over 2 is in the first quadrant. All right, so we know that that's now plus. So now we got to get the cosine. Well, this is that same sort of situation that we had before. where we know one of the trig function values, and we got to find one of the others. So we know the cosecant of x is equal to 6. From that, I can get sine. Sine of x is going to equal 1/6. So that's pretty quick. And then now that I know sine, I can get my cosine. So I'm going to go ahead and use the Pythagorean identity. We haven't done an identity method of doing this for a while. I know that sine squared plus cosine squared is equal to 1. So I'll put in the 1/6. So this gives me 1/36 plus cosine squared equals 1. Or cosine squared equals 35/36. And so then I get that the cosine of x is the square root of 35/6. But again, I don't know if this is plus or minus until I actually look into it. So the cosine of x is either going to be positive root 35/6 or negative root 35/6. All right, so how about that one? Is this one going to be positive or negative? Okay, so when you're saying positive, well, this time Mariola backed you up. I was waiting for her to be contrary again. Let's put a minus. All right, well, it turns out that this one is a negative. And I know what you're just thinking. Bruce, you just said all of these are going to be positive. And I did, but those are not what we're talking about. Here we're talking about the cosine of x. And x, we already saw, was a second quadrant angle. And in the second quadrant, cosine is negative. So I'm going to erase the little plus bit here. And we've got that the cosine of x is negative root 35/6. So just some things to realize here. I know that it's usually at about this point that people get really frustrated with the plus and minus, you know, the positive and the negative. And there is a lot we have to pay attention to. And worse here with this half angle stuff is some of the angles are in different quadrants than the other ones. And so we really have to be paying attention to where they are. Okay, so Amber just said, can I explain how I got the quadrant again? So they told me part of the problem, they said that x was between 90 degrees and 180 degrees. So that was a given. So that tells me that this is the same as pi over 2 and pi. So that tells me that this is quadrant number 2. So that was given. But then I divided by 2 to find out where the half angle is. The half angle, we see that we get numbers between 45 degrees and 90 degrees, and that's quadrant 1. So that's how I know that the half angle is in quadrant 1 and the original angle is in quadrant 2. So is that good, Amber? Does that make sense? Yeah, okay. All right, well, now that we've got that cosine, we can go ahead and plug it into the formula for the half angle. So I'm going to leave that up on the board because that's going to be important here later. So from this then, we get that the sine of x over 2 is going to equal the square root of 1 plus root 35/6 all divided by 2. And notice that it's a plus now because we are subtracting a negative. All right, so this is the value. We probably should clean it up a little bit. If I multiply everything in here by 6 to get rid of that complex fraction, I'm going to get the square root of 6 plus root 35 all over 12. If this were an exam or a quiz, this would be more than sufficient for me. I'd give you full credit for that. I have a feeling that the computer probably wants you to rationalize. To do that, we need to get this thing to be a perfect square. So I'd multiply it by 3. And so this then would give us the square root of 18 plus the square root of 35. And that's all going to be divided by 6. We get the square root of 36 on the bottom, which is 6. So I'm guessing this is how the computer is going to want it. But like I said, actually, I would have been fine with this step above here, even with the complex fraction in the root, because I don't really care that much about simplifying at this stage. At this stage, more I want to see that you can get the value. All right, so there's the sine of the half angle when the original angle had a cosecant of 6. All right, so there's the first part. For the other two, we're going to do exactly the same thing. We're just going to use their formulas. So I don't think I'm going to go all the way through it, but let me just kind of talk it through. So if we're going to do, say, cosine of x over 2, again, that one's going to be a plus or minus, but this time it's 1 plus the cosine of x over 2. And to do this, we need the cosine of x, but we already have that. Remember that we calculated over here. We can still use that same value. We're going to put that in here. And then again, is this plus or minus? The answer is it's plus, because the half angle is in the first quadrant. And so all its trig function values are going to be positive. So this would end up being the square root of 1 minus root 35 over 6 divided by 2. Again, simplified to your heart's content. Oops, all the way over 6. And then lastly, for tangent, well, you just use the tangent formula, which is the square root of 1 minus cosine of x over 1 plus cosine of x. And again, plug this number in for cosine of x.
I have a question, Bruce.
Sure.
On the homework videos, for tangent, they just went ahead and divided the answer they got for sine by the cosine. Do you think that's something that you'd be okay with on a test, or do you want to see the tangent one worked out?
Okay, so Juan, same kind of answer I'll give you with like the other ones. I don't really care as long as you get to the correct answer, and tangent being sine over cosine is totally fine. And in fact, the formula that we get for the half angle of tangent, that one we also get by taking the individual sine and cosine ones and dividing. So either way is fine. But I do want to show you another technique that we could use to find tangent of half angle using one of the different identities. So hopefully that kind of answered your question. But yeah, it's totally fine. There are usually more than one way to get to the same answer in trig. In fact, there's usually lots of different ways. So as long as you're doing something valid, I'm not going to care too much that you chose a different path than what the book shows, what I show, or anything like that.
Okay, sounds good.
Okay, cool. And then Amber, I did see your question here. Would tangent be positive or negative? What's the answer to that, guys? Is the tangent of x over 2 going to be positive or negative? All right, so Diego just threw in positive, and that's absolutely right. It is going to be positive because, again, remember, the half angle, I wrote it as x, it should say x over 2. The half angle is in the first quadrant. All trig function values in the first quadrant are positive. So as soon as we saw this, as soon as we saw that that half angle was in quadrant number 1, we know all of the trig function values are going to be plus. Okay, so for the half angle for tangent, there you may remember that there were some other identities that we could use. Let me remind you of them because they're kind of nice in this situation. There were 2 other forms for that. So we had the tangent of x over 2 is equal to sine of x over 1 plus cosine of x. And the other form was 1 minus cosine of x over sine of x. And I would actually choose to use one of these for finding the half angle for tangent for 2 reasons. One, now I don't have to worry about plus or minus signs. The plus or minus aren't here, so I'm going to get whatever these values tell me. And the other reason I would use these is they require me to know sine and cosine, and I already have those values. I just calculated cosine because I had to have it for the other identities. But I also know sine. You may remember that was the very first thing we did with this cosecant is we just flipped it over to find sine. So what we could do instead, I'll use the second one just because it's easier to simplify. We're going to get 1 plus root 35 over 6 divided by 1/6. So the sine is 1/6. That was that. And then the 1 minus cosine, 1 minus the negative is 1 plus. And this one's really fast. You just flip the 1/6 over and multiply. And it gives you 6 plus the square root of 35. All right, so there would be the tangent of x over 2. And this is equivalent to whatever that nasty radical form would be if you use the that 1 minus cosine over 1 plus sine, or sorry, 1 minus cosine over 1 plus cosine inside the square root. Or if you were to take the sine and cosines that we calculated along the way and divided them, it would still be equivalent to this.
I have a question.
Yeah, go ahead, Amber.
So the answers that we are getting, this seems a little silly to be asking, but what are those numbers? Are those, like, what is the significance of what we're getting?
Okay, so if I were to draw a picture here, let's call this angle, this is the x over 2.
Okay.
So it's some angle, right? It's an unknown angle, but we know this. But now what I know, for example, this is the tangent. And tangent, of course, if we think of it as opposite over adjacent, that tells me that this side is going to be 6 plus square root of 35. And then the adjacent side is going to be 1.
Okay, I get that. Thank you.
Right? Yeah, and so now I know, well, if I know those 2 sides, I can figure out everything about this triangle.
Okay.
Right? I can actually even tell you what this angle is by doing, say, an inverse tangent. I could find the third side. So, you know, I don't know what the application would be. I can't think of it necessarily a specific application. But if there were ever a situation where you need to know something about an angle, but all you know is something about the angle that's twice as big, this is a way that you can get there, right? We found the value, everything about this angle, knowing one thing about an angle twice as large as it. So that's kind of what's going on here. So the same thing is in terms of the sine and cosine. You can kind of think of the same deal. Like if we had just used that sine number, whatever we found for that sine, we could have set that up as our opposite over our hypotenuse and then build a similar triangle. Okay, so what happened to the 1/6 years? I just divided by 1/6. When you divide by a fraction, remember that's the same as multiplying by the thing flipped over. And so then when I distributed, it gave me the 6 plus the square root of 35. So all I did was divide by a fraction. All right, cool. All right, any other questions on this one? And I'm trying to remember, William, you were the one that asked, I think, about this originally. Are you feeling better about where to go with this?
Definitely.
Yeah, okay, good. And yours, again, probably starts with different information, right? You may not have that the cosecant of x is equal to 6, but you're going to know something about x. And whatever it is, you follow the same kind of process. Get yourself to cosine. This is one where you got to get yourself to cosine for sure, because the half angle identities, all of them require cosine. All right, so we good? Any other homework questions, or are we ready to keep plugging along? All right, well, looks like we're good to keep moving. So good news, bad news time. So good news. Let's start with bad news. Always better if we have bad news. Bad news, we have more identities to do. All right, so we're actually going to start by developing a couple more identities. But the good news is this will be it. We've only got a couple more to get. And once we have those, we're going to be able to move on. And what I'll finally be able to do is show you some of the why we care about identities. I know that I've hinted at things that are going to be coming up in calculus. That's always hard to swallow, right? Oh, you'll find out in months. But I will actually show you some things right now that are places where identities help us do things. So Amber, real quick, you just asked if there's a sheet of identities I can upload on Canvas. Absolutely. I'll do that. I will write myself a note right now. That way I'm more likely to remember to do it. But yeah, I will go ahead and put an identity sheet up. And it'll have all of them. It'll have all of them that we've done so that you can reference them. Okay, so let's bang out these last identities. There are two groups. One's called sum to product identities, and the other is product to sum. And if you think like a mathematician, which is every name of anything is exactly what it means, the sum to products are going to take sums of trig functions, right? So like sine plus sine, and turn it into a multiplication product. And then product to sum just go backwards. We're going to take two things that are multiplied together, sine times cosine, and turn it into a sum or difference of trig functions. Okay, so they're exactly what they sound like. And we actually find them using the sum and difference of angles identities. So let me go to the board and we'll build the first of this group. All right, so the first set we're going to look at are the product to sum. And there are three of these. We'll go ahead and start writing them out so we know what we're going to have. But again, the name tells us that we're going to start with multiplication and we're going to end up with addition. So the three that we're going to get are sine of alpha times sine of beta, cosine of alpha times cosine of beta. And then sine of alpha times cosine of beta. So the product of sum, you'll actually see in the book, they'll give you a fourth one. Their fourth one will be cosine of alpha times sine of beta. I am not going to give you that one because you already have it. Sine times cosine, cosine times sine really mean the same thing. So there's no actual reason to have another one. And like any good mathematician, I'm going to be super lazy and not do something we don't need. Okay, so with these three, we're going to be able to deal with all of the product of sum. All right, so first things first, notice it's just involving sine and cosine. We do not have product of sum identities for tangents and secants and cosecants and all those other things. We could build them, however, we don't usually, we just leave it as these three. All right, so where do we get these? Well, it turns out it's kind of a cool little trick. What we're going to do is let's look at that difference of angle identity for cosine. We saw this forever ago, but we had this fact that the cosine of a plus b, let's keep it as alpha and beta, so alpha plus beta. So this one was cosine of alpha, cosine of beta minus sine of alpha sine beta. So this was the one that we saw the very first day when we did the, drew the picture of the circle with the line segment and we measured its length and all that, right? So we got these two the very first day. So alpha plus beta and alpha minus beta. And again, the only difference between them was that there was a plus sign instead of a minus sign. Okay, so hopefully you remember these, or at least remember having seen these. Again, this was the first one we built. It's alpha minus beta, and then everything kind of fell. Well, here's what we're going to do with these. We're going to literally add these equations together. So we're going to get cosine of alpha plus beta plus cosine of alpha minus beta. So that's what we get on the left. And then on the right, notice that stuff cancels. Those pieces with the sign, those things just cross off. And so what we're left with is 2 cosine of alpha, cosine of beta. So notice this second in our product of sum list, cosine of alpha times cosine of beta. That's what this right-hand side is, with the exception of that 2. So all we have to do to get our identity here is just to divide by 2. And so what we get for cosine of alpha times cosine of beta is 1/2 cosine of alpha minus beta plus cosine of alpha plus beta. So, as promised, it's a way to write a product of cosines as a sum. Yeah, that's it. At this point, it starts feeling a little anticlimactic, right? You're like, big deal. We just added a couple of things we already had and rearranged. But that's kind of the whole point of identities, is we start with things we already know and rearrange. All right, well, there's your cosine times cosine. Now, if you want to get, say, sine times sine, I want you to notice that we could actually use the same equations. Except in this case, instead of adding them, we're going to subtract them. Because if we were to subtract one of these from the other, the parts with the cosines cancel, but the parts with the sines combine. right? Because when you subtract a negative, it's the same as adding. And so what you get for the sines is very similar, except instead of adding those two things, we subtract them. So this is also a pretty common theme you're probably getting used to with identities, is that identities that are similar to each other often have similar forms. And in fact, very frequently, the only difference is a change in sign somewhere. And that's what we see here. Okay, so that's how we can write a product of sines as a sum. And yeah, I know it's weird that you get a sum of cosines, but well, that's how it plays out. All right, so lastly, what about sine of alpha, cosine beta? Now, clearly we can't use these identities anymore because we don't have a sine of alpha times a cosine of beta. However, there was an identity that involved sines times cosines, and that was actually the sum of angles for sine. So I'm going to try to recycle this a bit. The ultimate in laziness. But let's look at the sine of alpha plus beta. That was sine of alpha, cosine of beta, minus, or sorry, plus sine of beta, cosine of alpha. And then the one for the difference of angles looked exactly the same, except there was a minus. And both of these have a sine times cosine. And now that we've seen what the trick is, this is going to surprise exactly 0 of you. We'll go ahead and add those together. Again, this last term cancels. And notice that we've got 2 sine of alpha cosine of beta. So that's double what we want here. So we're just going to have to divide by 2. And so what that'll end up giving us, if you do just like 2 steps on this equation, you're going to get 1/2 sine of alpha minus beta plus sine of alpha plus beta. And it's a totally similar form. You look at these, the 2 above and the 1 below it, and it's almost identical. I mean, it's like, look at these two. The only difference is a sine or a cosine. But again, it fell from identities that we already had. All right, so there are your 3 product to sum identities. So let me just show you a quick example of where this could be used to help us simplify an expression. Actually, before I go there, any questions on how I built those? Hopefully the algebra makes sense. All right, so here's an example immediately where we can use the product to sum identity to help us out. So let's say through the course of something, you needed to calculate the cosine of 5 pi over 12 times the cosine of 7 pi over 12. Now, neither one of those angles are nice angles. We could calculate them. We could find the cosine of 5 pi over 12 and the cosine of 7 pi over 12 if we did some sort of a sum of angles kind of trick. But check out what happens if we use the product to sum. So let's go to the second one here. We've got cosine of alpha, cosine of beta. So these two angles are my alpha and beta. Which one's alpha and which one beta is beta doesn't really matter. Recognizing these first two, that alpha and beta, their roles can be swapped all you want because of the commutative property. So for the first two, you can let them be whatever you want. For the third one, alpha has to be the guy with sine, and beta has to be the angle with cosine. But since we're doing cosine times cosine, we can pick either one to be alpha, and the other one will be beta. All right. So let's do this. We need alpha minus beta. Since I can choose whichever one I want, I like to choose the bigger one to be my alpha, because then when I subtract, I get a positive number, and I'd rather have a positive number. The other piece is going to be the cosine of 7 pi over 12 plus 5 pi over 12. All right. I know that it probably looks uglier right now, but watch what happens. This is going to give us a cosine of 2 pi over 12. And the other one's going to be a cosine of 12 pi over 12. And both of these are nice angles, because the 2 pi over 12, that's the same as pi over 6. And 12 pi over 12, that's pi. And those are both angles that we know well. So in terms of what this is going to equal then, we're going to get 1/2 times, okay, so we need the cosine of pi over 6. Well, that's root 3 over 2. And then we need the cosine of pi. And the cosine of pi was -1. And so we've got an exact value for the cosine of 5 pi over 12 times the cosine of 7 pi over 12. I'm not going to leave it like that. I want to make it a little bit prettier. Basically, I'm just going to get a common denominator and do all that good stuff. But this ends up equaling the square root of 3 minus 4 all over 4. Not 4, 2. Square root of 3 minus 2, sorry, all over 4. And I promise you, had you started with figuring out exact values for the cosine of 5 pi over 12 and 7 pi over 12 using sum and difference of angles identities and then multiply, you'll get to the same place. This is just a lot faster, a lot easier to do. All right, so there are your 3 product to sum identities. And like I said, this is an example of where we could use it. All right, so we've got 3 more that we want to do, or sorry, not 3 more, 1 more set. And these are called the sum to product. So let's go ahead and just get those knocked out of the way. But real quick, because it just popped into my head, let me remember to do this. Code word of the day. Word of the day. I'm just looking around at what I got here, and really random. Word of the day today will be socks. I got a pair of socks right here. All right, so word of the day for today is socks. Let me go ahead and write that down so that I don't forget. All right, so word of today for May 18 is socks. Okay, so the last set of identities are the ones that are called sum to product. And again, they're exactly what they sound like. They're going to take a sum of angles and write them as a product, or sorry, a sum of trig functions and write them as a product. So we have 4 of these as well. We're going to have sine of alpha plus sine of beta. there's also going to be cosine of alpha plus cosine of beta. And then we're going to have sine of alpha minus sine of beta. And then lastly, cosine of alpha minus cosine of beta. So these we're really just adding the same trig functions, so sine and sine, or cosine and cosine. And when we say sum, these would really be the sum or difference to product, because you also allow for subtraction. All right, now I'm not going to derive these for you. I think you're probably done with trig derivation. But the way that these are found is actually using the product to sum and going backwards. So just for the sake of sparing us, I'm going to go ahead and just write out what these look like. So the sine of alpha plus sine of beta, it's going to be 2 sine of alpha plus beta over 2 times the cosine of alpha minus beta over 2. All right, so again, where that comes from, the product of some identities. If you're really interested, pop into my office hours or find some time when we can meet on Zoom, and I'll be more than happy to show you the derivation. But I think probably 100% of you don't want to see it. All right, so cosine alpha plus cosine beta, similar thing. You're going to get 2 times the cosine of alpha plus beta over 2 times the cosine of alpha minus beta over 2. So very similar form, but slightly different. And that's just because we're doing a different set of trig functions that we're adding. All right, so then we go to sine of alpha minus sine of beta. And again, you get something really similar. You get 2 times the cosine of alpha plus beta over 2 times the sine of alpha minus beta over 2. So I'm going to guess that you guys are starting to spot a pattern. Notice that every one of these things, we got a 2. And then we've got somewhere where we're averaging the angles. And then another place where we're getting half of the difference of the angles. And we've got just about every combination so far. So let's see if we can build what this last one is. So we're going to have a 2. And we're going to have some trig function of alpha plus beta over 2. And then some other trig function of alpha minus beta over 2. And then if we just look at what is the only combination we haven't done so far, well, that would be where we have sine of each. So if we just look at the patterns and go, okay, well then this is what it is. Here's your difference, or your sum to product for cosine of alpha minus cosine of beta. Yeah. Except that's not quite right. You got to hate this, where everything looks perfect. We got this great pattern, except it's not the positive of this, it's the negative. Don't blame me. I didn't come up with this stuff. This just happens that if you really go through the derivation, it turns out that that needs to be a minus. So this is like the first time in trig that we've run into one of these things where it doesn't really follow the pattern, which is a little dangerous because we fall into that trap of, oh, just follow the pattern. We see a pattern, it's good, it's good, it's good. Sometimes it's not. So just watch out for that. All right, so there are your 4 sum to product identities. And they're used in pretty much the same way as the product to sum. except going backwards. So let me just show you a quick example. And this one, let's do an algebra kind of example. We're going to just simplify this expression. So let's say we have the sine of 5x, and we're going to subtract from it sine of x. So one real quick word of warning. A lot of people, a lot of students make this mistake. I'm going to write it down and then I'm going to immediately erase it. So if you write this down, right next to it, incorrect or don't do this or bad or whatever to remind you. But a lot of times what people will do is they'll go, okay, cool, that's sine of 4x, right? Because 5x minus 1x is 4x. Please do not do this. Okay, please don't do this. This is totally bad. No, don't. Whatever you need to remind yourself, okay? Do not do that. I know you're going to want to. Some of you still probably will because it seems like that's how this works. But we cannot do that. In this case, we have to use the sum to product, and specifically, we're going to use this third one, okay? So do not do this, please. Fight that temptation. So instead, let's run to this and see what this tells us. So this is going to equal 2 times the cosine of, now here we do have to make sure that we use alpha and beta in the right order because subtraction is not commutative. So we're going to get alpha plus beta, so 5x plus x over 2. And then we're going to get sine of alpha minus beta, so 5x minus x over 2. So just go to this identity, the third identity, and everywhere you see alpha, put 5x, and everywhere you see beta, put x. Okay, well, let's see how this simplifies. 5x plus 1x is 6x, and divided by 2 is 3x. That's going to be cosine of 3x. The other one, 5 minus 1 is 4x. 4x divided by 2 is 2x. So this is actually what sine of 5x minus sine of x is equal to. Very different than sine of 4x. Okay, so you got to be really, really careful when adding and subtracting trig functions. Make sure you use the product or sum to product identities, not just add or subtract what's inside. All right, so there you go. There are your last identities. Okay, so as promised, I told you, hey, this is it. We're done with identities. We've built everything that we need, which is good, but it's rough. I mean, there's a ton of stuff. And when I post a sheet of identities, you'll see how big they are. So yeah, you just said, do we use... so do you use these for problems like the sum to product? Absolutely. What I'm going to show you, we're going to take a little break, but then when we come back, I'm going to show you some more identity stuff, confirming identities that involve these. And then I'll start showing you solving equations. And when we solve equations, we use these things all the time. Okay, so some of the where we can use them, just hold tight. We're not quite ready there. But we've built them all. We've got this huge list. Think of them as what they are. They're tools. These are tools to make it easier for us to do what we need to do, whether it's solving an equation, doing calculus, the stuff we don't even know about yet. That's really where we're going to use identities. Identities are all about changing the form into something that works. And I can't tell you when that's going to happen. I mean, and that's one of the problems. I can't just give you the, hey, in this situation, always, blah, 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 blah. But there are going to be lots of times when we run into something and go, oh, man, if we use this identity, then we can change the form and then it's easier to do. So you need to get familiar with the identities, not just be able to use them, but you need to start recognizing them, start recognizing their forms, and that's where they get useful. So that then later when you go, oh man, if I change that, like I've got a cosine of 2x, let's say, but if I change it into this other form, I've got only cosine, which then means I can do these steps faster. That's kind of where we need to go. Anyway, so let's take a quick break here. It's just about the top of the hour. So I'm going to hit pause. Okay, so let's play around a little bit more with these new identities. And we'll actually confirm a pair of identities that where we need to end up using these guys. So I'm going to go to the board because I already got one written up here. So let's look at this one. We've got sine of 3x plus sine of x over sine of x times cosine of x. And that equals 4 cosine of x. All right. So just like any identity, we want to start with the uglier side and manipulate it until it looks like the other side. So I think we can probably all be in agreement that it's the left side of this thing that's the gnarliest. So let's see where we can go with it. All right, so at this point now, we have tons of things we can do, like lots and lots and lots. Think about this fraction on the top. We could use a sum to product identity. We just developed one that's sine plus sine. On the bottom, we could use a product to sum identity. We have a sine times cosine. And we know that there's a way to manipulate that. We could also do things like the sine of 3x. We could make it a sine of x plus 2x and use a sum of angles identity. Maybe you recognize sine times cosine shows up in the double angle identity for sine. So we could do something there. I mean, there are a lot of things that we can now do. And this is what's going to be the challenge sometimes with these identities, is picking the right thing to do. And there is not really any best way of doing this. So my suggestion is just pick something and do it. So Amber basically yelled out to me on chat, sum to product. She gave me the exclamation. I think that's a good place to start. Let's take that top, sine of 3x plus sine of x, and let's use the sum to product on that. So we just developed this. Well, I just gave it to you. But this is the one that's going to be 2 times the sine of the sum of the angles divided by 2 times the cosine of the difference in the angles divided by 2. So just use the sum to product on top. So let's see if Amber steered us in the right direction. If it doesn't look like it, if it looks like stuff is getting not going the right way, we can always backtrack and try something different. And get ready for that to happen. When you're doing these homeworks, get ready for making a mistake and having to go back over it, try it a different route, because it will happen. All right, well, let's see what this gives us. So 3 plus 1 is 4, divided by 2 is 2. So we get 2 sine of 2x. And then 3 minus 1 is 2. 2 divided by 2 is 1. So this is what the sine, the sum to product with the sines did for us. All right, was that a useful first step? So Amber just said it doesn't work. Well, I don't know, it introduced a cosine. I definitely like that. Because remember where we're going, we need to have a cosine on top, so. I wouldn't be so quick to just throw it away. So then Amber said, yeah, but you can cross off those cosines. Yeah, that's true. I mean, if we keep going with this direction, the cosines do cancel. But that's not necessarily a bad thing. Because check this out, sine of 2x. Is there a way to get a cosine from that? Think about sine of 2x. There is a double angle identity for it. So I'll put it in parentheses here in red. But that right there, the 2 sine x cosine x, that's the double angle identity for sine. And now you guys should all be happy. Hopefully you see it. We cross off the sines. And we're left with 2 times cosine of x, which is our 4 cosine of x. So it turns out, Amber, you gave us a perfect first step. We just had to keep going, right? So sometimes it may not be really clear that you're moving in the right direction. So you might have to do a couple of steps. But notice what we did. So we took that idea of sum to product, which I think is a really good one, because since I've got fractions, the only way I can cancel things in a fraction is if I have products, if I have multiplication. If instead I had taken the bottom and gone product to sum, I would have had a sum over a sum, and those are really hard to simplify. So that's what about this algebraically makes me do this. I would have done the exact same first step. And then once I got here, you notice that I jumped into the sine of 2x, and that was on purpose, because going over here to the other side, looking where we're heading, I didn't want double angles. I wanted just plain old x, so I knew I needed to get rid of that double angle. That's what prompted this step. And of course, then algebra just sort of took care of the rest. So there were things about this that would have pushed me in the direction that we went. And I tell you these things mostly to try to just help you when you're doing it on your own, just some things to look for. So with fractions, you like products, you like multiplying on top and bottom. Start there. That's usually a good way to get yourself well on the way to the other side. All right, so there you go. There's an example of an identity that we are now able to prove. And I think you would all agree that if for some reason we had some sort of a real world situation that gave us this big fraction on the left, we would definitely want to be able to write it as just 4 cosine of x, because it's going to be a lot easier to deal with. All right, so there's that one. So let's try another one. Let's go with this guy. We'll have 2 cosine of 4x times the sine of x plus the sine of 3x equals the sine of 5x. Let me start wider here. So 2 cosine 4x sine x plus sine of 3x equals sine of 5x. All right, so let's see if we can take care of this guy. In terms of ugly, not ugly, I would probably say the left-hand side of this is a bit uglier. But let's talk about different things that we could do. So we definitely have multiplication here, so we could do a product to sum. We also, though, have this cosine of 4x. We could think of that as a double angle. That's 2 cosine, or cosine of 2 times 2x. So we could do like a double angle identity on that. We could split it apart, x plus 3x, and use the sum of angles identity for cosine. Similarly, for sine of 3x, we could split that into pieces. Same thing with the sine of 5x. So we do have a lot of choices. I say we start with product to sum. See what happens when we split this guy up. So we're going to get 2 times, and the product to sum formula for cosine times sine is 1/2. It's going to be the sine of x minus 4x, and then plus the sine of x plus 4x. So if you just go back and you look at what we talked about earlier today, that's what this identity is. We had the identity for sine times cosine. And so the angle for sine, the angle in the sine is the alpha, and the angle in cosine is the beta. So I just did what it said. Okay, well, let's just see what happens. So first of all, that 2 and that half cancel. That's always good. So we get a sine of minus 3x plus a sine of 5x plus the sine of 3x. And at this point, you should be a little excited because we now have a sine of 5x. And if you look at where we were going, that other side had a sine of 5x. So we now have at least what we needed over there. We also have some extra stuff. So somehow we got to get rid of those. All right. So how are we going to get rid of these guys? Thoughts? And if anybody says, take minus 3x and 3x and add them together to get 0, I'm going to throw my pen at you virtually. Don't do that, right? Remember, we can't just add those things on the inside. So any ideas how we can get rid of these? Nothing? Thanks at least for letting me know you're out there, Amber. She just said no idea. Well, do you want the easy way or the harder way? Okay, so Adam just said maybe a sum or difference. So the sum or difference would be the harder way. It's not terrible. But if you were to look, we just have these two that are being added. So what we could do is use the sum to product identity for that. Let me show you how that would play out. I'm going to do it both ways, just so you can see. But if I've got sine of minus 3x plus sine of 3x, and we go back to the sum to product, and this becomes 2 times the sine of these two angles added together and divided by 2 times the sine of the one minus the other divided by 2. That's a lie. That's not a sine. That's a cosine. So this becomes 2 sine of 0 cosine of 3x. And the sine of 0 we know is 0. So 2 times 0 times cosine is 0. So I know that those two things added together equal 0. So that was it using the sum to product identity, which was definitely the harder way, but it worked, totally worked. Okay, so let me show you what I think is the easier way. So instead of doing the sum to product, I'm going to recognize that sine is an odd function. Remember, all the trig functions are either even or odd. So this one I know is odd. So because it's an odd function, that tells me that the minus sign that's on the inside comes out as a negative. And so now I have negative sine of 3x plus sine of 3x, which of course also gives me 0. Oh, good Lord. All right.
So in this situation, technically we could add the sine of negative 3x plus the sine of 3x. We just had to make it look right first. Just it did, yeah, it broke your rule, but I get it's funny, you really do just add them together though.
Okay, so you just said technically we can. No, technically you cannot, because it, like, legally that's illegal. It did work out that you got the same thing, right? But that's like purely coincidence and all that. So you got to be really, really careful with these things, because sometimes it works out. But that's true about any kind of math. There are some times when what you want to do still works out, even though in general it's not an okay thing, right? So while yes, it would have played out, I would have just told you that had you written, say on the board, you had written, you know, sine of minus 3x plus sine of 3x equals sine of 0, I would definitely not have given you full points, right? So yes, it kind of played out this way that it worked,
Yeah.
but in general it doesn't. So
It works because sine is an odd function. That's only why. I just thought it was interesting that we did end up choosing one that was an exception.
yeah. The other issue, and I'm coming back to the board just because I want to kind of address this on the board. The other issue though, and this is where we have to also be really careful, is that with identities, we know where we're going, right? And since we know where we're going, there's a real tendency when we get to a place where we're like, well, crap, we don't know what else to do. You get here and you go, well, those have to go away because it has to equal sine of 5x. So the inclination is just to go, okay, cross them off. But with identities, the whole point of identities is not get me where you're going. It's show me how to get there, right? And you hear me talk a lot about like maps and driving when it comes to identities, because that's kind of my big analogy. But it'd be kind of the same thing where if I said, okay, you need to get to Reno, you would want to have a map. You would want me to tell you, okay, start on Highway 50. When you get to Carson City, continue on the freeway. Then when you're in Reno, get off at this exit, right? And that's what the identity is all about. You're telling me how to get there. You're not just telling me, well, yeah, you'll get to Reno. Okay, thanks. But I need to know how to get there. So especially when it comes to like exams, show me what you're doing. Explain what you're doing, because that's what I care about. I know it equals sine of 5x. That's why I even gave you the stupid thing to do, right? Is to show, is for you to show me how to get there. So that's just something to think about, that, yeah, sometimes what we hope will happen will happen. But watch out for that with identities. And the reason I'm warning you here is that if it's not an identity and you don't know where you're going, there might be situations where you cross stuff off or you combine things that would have worked potentially. It'll just end up causing troubles. So anyway, I'm starting to preach. I don't want to preach. But yeah, Adam, it does turn out that this one, just because of it's the even and oddness. It's because sine is odd. that when those angles are opposites, they will always cancel each other. You'll always get a 0. But that's really just because it's sine. If it was cosine, it would not have happened. Anyway.
Yeah, thank you.
Yeah, you're welcome. Okay, so identities. We are done with identities in as much as we're not going to prove any more identities, but we're definitely going to use them. Okay, so don't just think, well, cool, now that we're done with this section, we don't have to worry about identities anymore. And even beyond the next exams and quizzes and stuff like that, they're still going to show up the rest of the quarter. It's just we're going to use them from time to time. So we basically just have our tools now. We've acquired them all, right? We went down to Meeks and we bought all the tools that we need. Now we need to start using them for things. So the next thing that we're going to talk about, the first place where we're going to actually use identities for anything, is where we solve equations. So we're going to start today talking about how to solve trig equations. So a trig equation, of course, is just any equation that involves a trig function. And it can be something as simple as, say, cosine of x equals root 3 over 2. So just like any equation, whether it's a trig equation or a log equation, exponential equation, or a polynomial equation, or whatever, what we're looking for are the numbers that we can put in here for this variable so that this equation is true. All right, so we're basically just looking for what numbers can we put into cosine and get out root 3 over 2. So I chose one that we can answer, you know, using just information we've gotten so far, because this is a nice value for cosine. So go back and look at your chart, or if you've got it memorized, even better. Where is cosine equal to root 3 over 2? Okay, so Amber just put out pi over 6. Cool, thank you. So x equals pi over 6 is going to be a solution to this, because the cosine of pi over 6 is root 3 over 2. All right, but now this is where trig equations are a little bit different than other equations that you've done. And that is that this is not the only answer. Can you give me another angle, another number that we could put into cosine to get? Okay, so I got a bunch of people throwing out 11 pi over 6. If you guys were anticipating my question. But yeah, how about 11 pi over 6? That's the one that's in the fourth quadrant. It's also on our chart. Gives us root 3 over 2. Okay. But again, these are not the only solutions. There are more. Can anyone give me another one? And I'll tell you this, your chart's not going to be any more help. Because on your chart, there are only 2 angles that this works for, pi over 6 and 11 pi over 6. But there are more. Okay, so Adam, you just said past 360. First of all, don't you dare say degrees to me. Rude. No, I was kidding. But yeah, so what about past 2 pi? Can I put in a number bigger than 2 pi? And the answer to that, of course, is sure. I can put in a number bigger than 2 pi. I can put in a number smaller than 0. I can put in any kind of number I want. So if we don't restrict ourselves just to being between 0 and 2 pi, somebody give me another angle. All right, so Adam, you just said 13 pi over 6. Cool, thank you. There's another one. So we'll put x equals 13 pi over 6. And that one is actually coterminal to pi over 6. So if we were to come back, say, and draw our little picture here, we had an angle of pi over 6. So like right there. We also had the 11 pi over 6. So those are the first two that we found. So pi over 6, boom. But I could do another loop. If I do another rotation and I come back, that's 13 pi over 6. Well, I could do another loop, add another 2 pi, and get 25 pi over 6. Do it again, 37 pi over 6, 49 pi over 6, 61 pi over 6, and so on and so forth, right? I can just keep going around and adding 2 pi. So here's what we're going to do. To account for all of those, the one that was 13, 25, 37, dot, 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 right? All of those. What I'm going to do is I'm going to write plus 2 pi n. And what this is telling me, n is any old integer. Pick your favorite counting number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Also 0, -1, -2, -3. Okay, that's any of those. So what I'm doing here is I'm just adding on any multiple I want of 2 pi. Well, you can make a similar argument for the 11 pi over 6. That was this one. But I could add another 2 pi, 4 pi, 6 pi. I could subtract 2 pi, subtract 4 pi. And so we'll do the same thing. And we'll write plus 2 pi over n. So this right here is a list of all of the solutions to cosine of x equals √3/2. And this is definitely different than what we're used to, right? Because what we're used to, we just get our x equals, we put a box around it, and we're done. But now, because the trig functions are periodic, because they repeat, we are going to get an infinite number of solutions. This list never ends. And the way that we show it is by adding the plus 2 pi n. Now, if we were asked, okay, find all of those, all the solutions to this that are in between 0 and 2 pi, for example, well, then our list would have just been pi over 6 and 11 pi over 6. But in the absence of somebody telling us target location, to be inclusive of all of the answers, we have to add on this plus 2 pi n. All right, so here's going to be the difference now. When we solve trig equations, we need to make sure that we add on some sort of piece here to account for all the other ones as they repeat. All right, well, let's take another guy. We'll do a similar one, and except instead of cosine, let's use tangent. We haven't used tangent in a while. So let's do one with tangent here. So let's do the tangent of theta equals -1. Okay, so again, let's get a list, a complete list of solutions. I want all the solutions. All right, well, look at your chart. Can anyone give me n angle whose tangent is -1? All right, Mariola just put up 3 pi over 4. Perfect. Okay, so we know that theta equals 3 pi over 4 is definitely a solution. And then Kiva just put up 7 pi over 4. That is that other one. So tangent being negative means we're in either quadrant 2 or 4. So 3 pi over 4 is the quadrant 2 angle. 7 pi over 4 is the quadrant 4 angle. All right, But those are only the ones that are between 0 and 2 pi. And of course, if we want the others, we need to be coterminal. So we can add plus 2 pi n to each one of those. And now everything is on our list. So like basically, if we were to write out all the different numbers here. So let's see, we have 3 pi over 4, 7 pi over 4. Adding 2 pi to this would be 11 pi over 4. Adding 2 pi to this one is 15 pi over 4. And if we kind of continued with that, we get 19 pi over 4, 23 pi over 4, and dot, 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 dot. All right, but there was a reason that I wrote it this way, because I want you to notice that there's a pattern. Look at these numbers. Obviously, the bottom is always 4, right? There's always a pi. So we'll put that on top. But look at these numbers on top. 3, 7, 11, 15, 19. What's the pattern? How do you move from one to the next? Okay, so Amber just said you add 4. Okay, so what I'm going to do is I'm going to, if I start with this first one, 3 pi over 4, I have to add 4/4 of pi. And notice that those 4's cancel. And what I'm left with is 3 pi over 4 plus n times pi. And this is actually how I'm going to represent the answer, because like any good mathematician, I would rather just write one line instead of 2 lines. But honestly, I did this for another reason. I want you to notice something. So 3 pi over 4, that was the first angle we ran into. But now what I'm doing is I'm adding n times pi instead of n times 2 pi. Well, there was something kind of important about tangent that had pi in it, and that was its period. Remember pi's period, or sorry, tangent's period was pi. So notice what I'm doing here is I'm adding a multiple of the period. I'm taking one value and I'm adding a multiple of the period. If you go back to that one with tangent or with cosine, you'll see that I'm adding a multiple of its period as well. It's 2 pi n. But again, I'm finding all of the solutions that are in one period and then adding a multiple of the period. So let me write that down because that's kind of big. So here's what we're going to want to do in general. You're going to find all values in one period that are solutions. Then what you're going to do is you're going to add a multiple of the period to each one. So my plan here is to give you the, here are how you solve trig equations. And so what we're seeing is that this is really what we need to start with. We start with, okay, I've got sine equals. Find all of the solutions in one period and then add multiples of the period. And that's true whether it's cosecant or cotangent or whatever. Okay, we're going to find the solutions in one period and then add the multiple. So let's do one more before we call it a day. We're definitely nowhere near done talking about equations. Okay, so we'll pick this up on Wednesday. But let's just do one more here. Let's take a sine. This way we've done one of each of the big three. So let's say we've got sine of theta equals -1. So first things first, we want to find all the values in one period that are solutions. So since sine has a period of 2 pi, let's find all of the numbers between 0 and 2 pi, where sine is -1. So you can go ahead and look at your chart. And if you go down your chart, you'll see that sine is equal to -1 at 3 pi over 2. And that's the one and only place between 0 and 2 pi where we get a sine equaling -1. So there was step number 1. We found all the values in one period. Okay, so now we're going to add a multiple of the period to each one. Okay, well, the period for sine is 2 pi. And then we need to make it multiple. So we'll put 2 pi in. So go ahead and circle it, box it. But there is the list of all of the values that will make that equal -1. Okay, so this is the general process when we've got a trig function equaling a number. So what I'll show you next time, we'll do an example where it's not a nice angle, where it's not something on our chart. And then we'll turn our attention to equations that are uglier, that require more, because they don't always look this simple. And that's where things like identities are going to be helpful. Okay. So Amber's already anticipating where I'm going next. So is there a quiz on Wednesday? No, I'm going to give you a week off, just to give you kind of heads up of where we are and what's going to be going on. So Wednesday, we'll pick up this conversation and do more solving equations. And then once we're done with that, we're going to start doing actual trigonometry. We're going to start dealing with triangles, finally. But that's where we're heading. Next Monday, a week from today, there is no class because it's Memorial Day. So we're going to get a day off, whatever that means. But it means it's a day of me not sitting in front of the computer, which I'm definitely up for. But so what we'll do is we'll just have a quiz the following Wednesday. So we'll talk more about that next time, but no quiz for Wednesday. All right. So the only thing you should be working on from today to Wednesday is keep going on the homeworks. Make sure you're practicing identities and the like. Okay. All right. So any other questions before we sign off? All righty. Okay. So everyone have a great couple of days, and I will see you on